Hello students, so welcome to part 13, where in this part 13 we will look into combustion, theoretical and excess oxygen and air. So previously we studied about theoretical and excess reactant in general reactant in reaction. In combustion we will look more on the theoretical on oxygen and air. Okay, because why is oxygen and air important? Because oxygen and air is actually one of the reactant in combustion. Combustion happens when we have reaction between fuel and oxygen. So that's why oxygen and air is important in combustion. Okay, in combustion, normally oxygen and air will be used as the excess, will be made into the excess reactant because oxygen and air is cheaper than fuel. Okay, what is the relationship between oxygen and air? Okay, if we look into the composition of air in mass balance class, so we will use in mass balance class we will use 21 mole percent O2 and 79 mole percent of N2. This is our air in this class, but actually it has other compounds, but in general by default we just use 21 mole percent of O2 and 79 mole percent of N2. So we see that this is the relationship between O2 and air. This relationship between O2, N2 and air can be written like this. Number mole of O2 is equivalent to 0.21 mole times by 21 times number mole of air. So if you want to find number O2, we just remember this equation, 0.21 times number of air, number mole of air. If you want to find number mole of N2, nitrogen, is equal to 0.79 times number mole of air. So we'll get number mole of nitrogen. Okay, please remember this equation, this relationship, because probably in later when you try to solve mass balance in combustion, in terms of combustion, you need to use this relationship. Okay, sometimes you may encounter questions using this information, 3.76 mole N2 divided by mole O2. Okay, this information actually comes from the this, where 79 mole N2 divided by 21 mole of O2, then we'll get 3.76 mole N2 per mole O2. Because if you look into the textbook, sometimes you will encounter this and probably you do not know where this number comes from. It actually comes from this relationship. Okay, what is theoretical oxygen? Theoretical oxygen is defined as N, number of mole or molar flow rate of oxygen needed for complete combustion of all fuel fed to the reactor. Okay, what it means here, the sentence is, we assume that all C in fuel is oxidized to CO2, all H in fuel is oxidized to H2O, all S in fuel is oxidized to SO2. Okay. So to find theoretical oxygen, this is the definition. Theoretical air is the quantity of air that relates to theoretical oxygen. For example, we have CH4, a fuel, which is 100 mole, and this is a reaction for combustion. Okay, if we have 100 mole of CH4, how many mole of theoretical oxygen? If we have 100 mole to react complete process of this complete process, how many mole of theoretically O2 that we require? So theoretical O2 to completely oxidize this C and H, 100 mole of CH4 times with this the stoichiometric ratio between CH4 and O2. So we will obtain, if we have 100 mole of CH4 and it requires 200 mole of O2 as theoretical oxygen for the process to completely to become complete combustion. Okay. So once we get theoretical O2 as 200, we need to find how much is the theoretical air that relates to 200 mole of O2. Therefore, we can use this equation where we know just now number of mole of O2 theoretical equivalent to 0.21 times the number of mole of air theoretical. So we solve this and we obtain, if we have 200 mole of O2, that means it comes from 952.4 mole of air. Excess air is amount of air fed to the reactor exceeds theoretical air. Okay. Percentage excess of air is given by this definition, this equation, N air fed minus N air theoretical divided by N air theoretical times 100. Then you'll get your percentage excess of air. This equation can also be used for, instead of using it here air, we can use it here O2. For oxygen, replace air with oxygen, replace air with oxygen. So you know, if it's for oxygen, then percentage excess of oxygen will be N oxygen fed minus N oxygen theoretical divided by N oxygen theoretical times 100. So these two equations can be changed into O2 if you need to use in terms of O2. Okay, for example, I would like to give you an example how we use excess air. How do we use this and this using this example? Okay, so this is the same example that we used just now, which we find the theoretical air. Okay, so we have CH4 oxidized producing CO2 and H2O. So theoretically, if we have 100 mole of CH4, we require 200 mole of O2, and this 200 mole of O2 must come from 952.4 mole of air. But okay, let's say like this. In actual case, you have only 100 mole of CH4, but your air fed into the process is 1904.8 mole of air. Definitely, we excess the amount of air that we require, right? So definitely we have excess here. Okay, to find the percentage of excess of air, what we use it using this equation, put it here, number of mole air fed, actual, minus by theoretical mole of air, divide by theoretical mole times 100. So after we do the calculation, we get it is 100% excess air. Okay, and then I would like to focus on this equation. Okay, and air fed equivalent to excess times with mole of air theoretical. See, let's say if you know amount of excess and also amount of theoretical air, for example, you can find number of mole of air fed. For example, in this case we have 50% excess. We know we have excess in terms of air as much as 50%. So it becomes here, this X changed to 1.5. That's 1 is initial, 1 is the original condition. 0 plus 0.5 becomes 1.5 here. This 0.5 actually comes from the excess. So 1.5 times the amount of theoretical air that we know, we will find the amount of air fed into the process. So this equation is also important for mass balance later.